Hello everyone, this is section 4.5. We're still on logarithms, so let us do college algebra. Logarithms. Alright, so let's see. Let us begin with some of these problems. So all I have is this one page, that's all we're going to do today. So let's start off with some review problems maybe. Let's start off with this one right here. What is that going to equal if we want to evaluate that? Here's a cool sentence. Logs are the power we raise the base, that's the 4, to get the argument. That's always the argument right there. You can put that in parentheses if you want to. So logs are the power we raise the base to get the argument. So 4 to the what power gives you 16? 2. And here's a little check if you want. If I convert this to its equivalent exponential form, notice I do get a true statement. What's my equivalent exponential form of this log form? The base is 4, so that's going to be my base for exponential form. Logs are equal to the exponent. Logs are equal to the exponent. So in exponential form, isn't that where the 2 goes then? And then equals whatever's left, the argument. So yeah. What is this one going to be? Same idea, evaluates. So logs are the power you raise the base to get the argument. 4 to the what power gives you 4? 1. And here's the equivalent algebraic form, or exponential form rather. What's my base going to be for my exponential form? The same as that base, which is 4. So 4 to the, what's my exponent going to be for exponential form? Isn't that the exponent, that 1, because logs are equal to the exponent? So I'm going to put the 1 right here. And then equals whatever's left, which is the argument 4. And isn't this a true statement? Indeed it is. 4 to the 1 equals 4. In fact, that's a log property. Whenever the base of a log is the same as the argument, the answer is always going to be 1. Here's another property of logs. If the argument of a log is 1, you don't have to think about it. The answer is going to be 0. So again, whenever the argument of a log is 1, it doesn't matter what the base is, the answer is always going to be 0. And you can see that when I convert this to its equivalent exponential form. Let's see, so my base is 4. Logs are equal to the exponent. And then equals whatever is left, which is the argument, which is 1. And is it not a true statement? 4 to the 0 equals 1. So indeed, these properties are cool. Oh, the next one's a little tricky. Remember, the domain of any basic log function or log expression, as this is an expression here, since I don't see f of x equals, whenever you can't have an argument 0 or negative, because the domain of any basic log function is x is greater than 0. In fact, here's a basic log function right here. And this is a log function here. Notice it's basic, there's no transformations being applied here. And notice when I graph that, this is what the graph looks like. All basic log graphs have this shape, with x equals 0 is always a vertical asymptote for all basic log functions. It doesn't matter what the base is, whether it's e, as this is, or 5, or whatever. This will always be an x-intercept for all basic log functions. Remember when we said the argument is 1? I said this 2 minutes ago. If the argument is 1, isn't that the x coordinate? If the argument is 1, the answer is always 0. So that's why this is always a x-intercept for all basic log functions. And what's the domain of this basic log function? 0 to infinity, or x is greater than 0, however you want to say it. So notice, this is a rounded parenthesis, so it's got to be, x has to be greater than 0. That's why you can't have an argument which is 0 right here. And for that matter, isn't this one not allowed either? Under the real number system, you cannot have an argument for a log which is 0 or negative. So these two then are both not in the real number system. Not in, I'll just write not in the real number system. Okay. Okay, this one's so interesting. It's okay. What's the range of all basic log functions? Don't I have the range as all real numbers? That's always true for any log function, even if transformations are being applied to it. The range for any log function is all real numbers. Remember, logs and exponentials are inverses of each other. What was the domain for any exponential function? Wasn't it all real numbers? And that means the range for any log function is going to be all real numbers, because that's how inverse functions work. They flip-flop the x's and the y's, or the domains and the ranges. They flip-flop as well. In fact, what was the y-intercept for all basic exponential functions? Wasn't it 0, 1? Isn't that the flip-flop of this 1, 0? Because again, if an ordered pair, like say 1, 0 is on one function, what's going to be on the function which happens to be the inverse of that function? The flip-flop of that ordered pair, 0, 1. Anyway, let's continue here. So this one's a little tricky, but remember, the answer or the range is all real numbers, so this does make sense. We should get an answer here. What is x going to be here? We want to solve for x here. So we want to solve for the argument. This is a weird question here. What is that argument? What must it be then? We can solve for that. Keep in mind, logs are the power where we raise the base to get the argument. So 4 to the what power gives you x? Well, we're given the exponent as -1. So I'm going to convert this to its equivalent exponential form. 4 is my base to the -1 is the exponent equals, and that's going to be the argument, x. And what is 4 to the -1? We know how to handle negative exponents. Isn't that 1/4? Or 1 to the 4 to the +1? How do you handle negative exponents? You flip over the base. This base is in the numerator here, so I put it in the denominator, and then make this exponent, whatever it is, positive. So 1/4. You don't have to really write that exponent 1 there, but if you want to, you can. Okay, so that's the answer. The argument is 1/4. I'll just write x equals 1/4. That's the answer. Okay, let's continue. These are using the log properties from this section. And this is very powerful. This is actually the property right here. If you have a log which has a base, which I call the generic a, and the argument is an exponential, and it's got that same base, and it's being raised to a power, then the answer is just going to be that exponent. So when you have a log whose argument is an exponential, remember, logs and exponentials are inverses of each other, and it's the same base, then the initial input, which is the exponent, r, will equal the final output. This is really composing inverse functions. I think on my lesson plan I show it. Let f of x equal log x, and let g of x equal a to the x. And then when you compose them, you'll get this idea. So it's not surprising, because a log and an exponential are inverses of each other. So if you have an argument of a log, which is an exponential, the initial input will always equal the final output, assuming these bases are the same, which they are here. So isn't this, we have a log whose argument is an exponential. I can put this in parentheses if I want to. This is the argument. And isn't the argument an exponential? We have a base being raised to a power. And aren't these bases the same, 4 and 4? So you can't help but feel like a genius answering this right off the bat. What does this equal? It equals 22, whatever that exponent is. Because again, we got to realize this is composing inverse functions. So the initial input, which is the exponent, equals the final output. What is this one going to be? Again, if you don't see a base here, it's assumed to be 10. I'll put it down there just for fun. And I'll put this in parentheses, the argument. So you got to recognize it when you see it. We have a log whose argument is an exponential, and it's the same base, 10 and 10. So the initial input, which is the exponent, equals the final output. So again, look how quickly we can do these problems. Very powerful how logs and exponentials are inverses of each other. Let's see. Let's try this one. Notice this is a little different. We have a base being raised to a logarithm power. And isn't it the same base, 4 and 4? So in this case, we're composing inverse functions the other way, the other order. And the initial input, which is the argument, equals the final output. So I'm going to put an X there for the answer since that is the argument. And here's the property I used right here. So notice when you compose inverse functions of a log and an exponential, it can either look like this form or that form. So be familiar with those two different looks. And when you see those two looks, you got to say to yourself, oh, that's what happens when you compose a log and an exponential. It's either going to look like this or it's going to look like that. And this one looks like that form. And again, very powerful when you compose inverse functions. The initial input equals the final output. Here's another one of this form. We got a base being raised to a logarithm. And isn't this, I can rewrite that as this. Isn't ln mean the same thing as log base e? And rewrite the argument? Now it's more obvious, isn't the base is the same? So what's the answer going to be? When you compose inverse functions, the initial input, which is the argument, equals the final output. So I'm going to write 6 minus x as my answer. What is this going to equal? Again, you don't see the base there, but it's assumed to be 10. So notice the bases are the same. So the composing inverse function, so that means that our answer here is going to be 18 because we're composing inverse functions. We have a base being raised to a logarithmic power. So that means the initial input, which is the argument, equals the final output. So those are easy. What about this one? Here's the directions. We want to write this as a sum and or difference of two logs. So let's use our properties and there are so many properties of these logs. If you have an argument which is a product, I can write it as a sum of logs. So I'm going to go like this. Log base 5 of 25 plus log base 5 of x. And we can simplify that. Can't that be simplified right here, that first term? Logs are the power. You raise the base to get the argument. 5 to the what power gives you 25? 2 plus log base 5 of x. So that's the final answer there. It comes from this property. Log of AB equals log of A plus log of B. So notice, a single log, you can write it as two logs, where you add the logs. These properties go both ways. If you have that, you can write it as a single log, where you multiply the argument since we're adding the logs. If we were subtracting the logs, you divide the arguments. Okay, let's see this one. What is this one going to equal? Let's use our property of logs, so I can write it as this. ln of e plus ln of x. So again, a single log, I can write it as two logs where I'm adding them since the argument is a product. It's e times x. I know that looks weird, but it's e, which is a number, 2.718 roughly, times x. We can simplify that. ln of e, I'm going to write it like this, log base e of x. Isn't that the same thing? Whenever I see ln, I like to write it as log base e. Oh, the argument's e, not x. Let me go like this. Plus ln of x. And now this can be simplified. We got to simplify if we can. Isn't this one of the properties? If the argument is the same as, if the base is the same as the argument, the answer is going to be 1 because e to the 1 power equals e. So I'm going to write it as 1 plus ln of x. That one's done. Let's do this. Write each expression as a single logarithm. So now we got two logs. So we're going the other way. Let's go the other way. So let us see what we get here. So for this one here, the trick is, so we've got two logs. We want to write it as a single log. Before we just do that, let's make it more compact. And it's more compact if you have a coefficient to make it as an exponent on the argument. And it comes from this property here. If you have a log whose argument as an exponent, it's a wild property. You can bring that exponent out as a coefficient or a factor in front. And so that's a true statement. And it goes this way too, the other way. In fact, I think we're doing it from here to here in our example. So if you have a coefficient, you can bring it as an exponent on the argument. So let's do that here. So I'm going to bring that 3 as an exponent on that argument x. So I have that, and I did the same thing here. Okay, now it's more compact. Now let's use the property of logs. Let's write it as a single log. Since these two logs are being added, let's write it as a single log. So I'm only going to write the log once. I'm only going to write the word log once. And then I'm going to multiply the arguments. So we have, let's see. Oh yeah, I wrote 2 to the 4th is 16. And now let's write it as a single log. And what's 16 times x cubed? 16x cubed. So that one problem is done. Let's move on to the next one. Again, 2 logs, let's write it as a single log. Again, let's do that trick, make it more compact. Put that 2 as an exponent of the argument because of that log property. So we have this, and then how do you handle it when you're subtracting 2 logs? Write it as a single log and divide the arguments. This one over that argument. So that one's done. Let's use change of base formula. If we want to solve this, your calculator doesn't have a log button with a base 3, only log buttons with base 10 or E. So we want the good base. By the way, I just did this for fun. If the problem were log base 3 of 27, you could answer that without a calculator. The answer is just going to be 3 because logs are the power you raise the base to get the argument. 3 to the what power gives you 27? 3. But notice 21's not a power of 3. So how are we going to handle this? Because we can't use a calculator because there's no log button with base 3. Change the base formula. Very easy to change this expression where the base is either 10 or E. I did E here for my first example. So how do you do it? You change that base, that bad base to a good base, E or 10, and then the argument's always going to be the same as that argument, and then over log with that same base you chose here, and then what's the argument going to be? Whatever that base is. And now you can type this in your calculator, and you get that as your answer. Notice I could have done base 10 as well. It's kind of interesting that these give the same answer. And then finally, log graphs. What is this graph going to look like? And this is very straightforward. Any log graph, which is a basic one, is going to look like that. X equals 0 is always the vertical asymptote. Isn't that interesting with the exponential function? Didn't we have a horizontal asymptote, y equals 0? Again, the flip-flop with inverse functions. And here's the domain, 0 to infinity. And the range is all real numbers because this is going to the right but also up forever. And then I did one more log graph. What about this one? What would this graph look like? So this does have a transformation. A vertical shift, that +1 is, since it's in right field. So let's graph it in stages. And I did the basic graph, which I did over here, ln of x. And now the next one, let's do the vertical shift. So notice I add 1 to all previous y coordinates. So that's why that 1, 0 becomes 1, 1. Vertical shifts don't affect vertical asymptotes. So that's why it's still x equals 0 for the vertical asymptote. And then what's the domain and range of this final graph? Right there. All right. Good. Bye-bye, everyone.